On behalf of Case Center for Electrochemical Sciences and Case Institute and Case Western Reserve University, I'd like to welcome you to the first of the Diamond Shamrock Lectureship Series for 1982. First, a few words about this lectureship. The first occasion of the lectureship was in 1977, and this is the third time now this year. The lectureship has been made possible through funds that have been given to Case Center for Electrochemical Sciences by the Diamond Shamrock Corporation. The objective of the lecture series is to present a series of lectures that bring together both academic and industrial electrochemists. And in fact, the lectureship is not only a series of lectures, but it is indeed a prominent electrochemist in residence for a period of, in this case, 2 weeks. And it's indeed a great pleasure to have, as the 1982 holder of this lectureship, a very distinguished electrochemist and chemical engineer, Professor Charles Tobias. A few words seem appropriate about Professor Tobias's background. He is a native of Budapest, that is Hungary, and indeed it's been one of my pleasures to visit Hungary with him for a part of a day or so in the vicinity of Budapest. He came to the United States in the late 40s, and he spent most of his professional career in the United States at the University of California. From the period 1966 to 1972, that is at Berkeley, he was chairman of the Chemical Engineering Department, and in fact has, in all of his period at Berkeley, been outstandingly known throughout the world for his work in electrochemical engineering and related areas. Some of his research accomplishments and studies include such areas as ionic transport with free and forced convection, the question of gas evolution in electrolytic cells, the conduction in heterogeneous systems, including bubble fields and electrolytes, work with porous electrodes, both fully and partially flooded. He was among the first, he and his group, to use high-speed digital computer techniques for calculating current distribution in cells and generally for simulation purposes. Other areas of his activities have included the non-aqueous electrolytes, realizing the importance of these electrolytes, in fact, well in advance of most of the academic and in some of the industrial world, particularly concentrating on non-aqueous electrolytes such as propylene carbonate. Studying alkali metals in these systems, and in fact coming up with methods for recovering alkali metals from organic solvent systems. And I think we should also take note of his work on ozone and the efforts to develop electrochemical processes and the like for producing ozone. Professor Tobias's impact on electrochemistry is very great through his scientific and engineering contributions to this field, but he has also made an equally great contribution, and in some of our dimensions maybe a longer perpetuating one, through the number of students who've come through his laboratories. And yea, if there was a person in the United States whom we could sort of call the grandfather of most of the active electroorganic chemists in the area of the, or the father at least, but he's getting second generations now. I think in electrochemical engineering it would have to be Professor Tobias. Indeed, much of the formalism of the subject has evolved through his efforts and his students, and perpetuates through his many, many students, some of whom are to be found on our own campus here and in the greater Cleveland area. So I, as an educator, have a special appreciation of the tremendous impact he's had through this channel. And then he's had a third area through which he's had impact, because he's done a lot in the way of professional and national and international service. Presidencies of societies, the Electrochemical Society, the International Society of Electrochemists, serving on many prominent committees which really were hard-working committees, some of which I've had the privilege of serving with him as the chairman, and he knows how to get his committees to work. Well, Before introducing or finally passing the program over to Professor Tobias tonight, I'd like to call attention to the fact that he will be presenting 4 formal lectures during the coming week and a half or 2 weeks. The first of them is this evening. There's another one on Wednesday, and a third one on Friday, and then the fourth one the following week. And they will cover such topics as, on Wednesday, current distribution on electrode surfaces, in a lecture in which we will follow it with a meeting of the local section of the Electrochemical Society, and there will indeed be a dinner and held here in the Circle Inn, and then another lecture by Al Salkind on electrochemical aspects of bacterial sterilization and wound repair in the evening at 7:30. And then on Friday, Professor Tobias will again lecture on mass transport in electrochemical cell processes, again in this room at 4. And then the following Monday, physical processes in electrolytic gas evolution, also in this room. And then just one more point. We have the privilege of having with us here this evening the industrial members group of the Case Center for Electrochemical Sciences, plus a number of other people from industry, from companies with whom we strongly interact in electrochemistry. And for those of you who are in this special group and have had pre-arrangements made, there is a reception and a dinner starting at 6 o'clock in the Garden Center, with a bus picking up those people who had these special arrangements at 5:45 here, and then also any stragglers who are at the Circle Inn at a few minutes before 6 to take them over to the Garden Center. Well, I think at this stage I'd like to finally turn the program over to Professor Tobias, whose topic for this evening is a perspective of electrochemical technology. Charles.
I was told that I have to wear this because for posterity my performance will be recorded. I thank you for your very generous introduction, Ernie. I enjoyed it so much that I thought you should just go on, and I will listen to it. I would like to talk to you today a little bit about sort of a perspective which includes the past, the present, and something about the vision of the future of what is broadly described as electrochemical technology, but which is largely based on transformations of the type where a chemical change is followed or accompanied by an appropriate flow of electronic charge and vice versa. Now, the discovery of electricity and the following exciting decades in the 19th century involved the generation, the storage, and the use of electricity exclusively by electrochemical means. In fact, the beginnings of electrochemical technology far preceded the discovery of rotating electric machinery. So the power sources for plants, mostly for electroforming and electroplating, were batteries. And all the impetus for developing both electrochemical science and better batteries came through this application. Only in the last decade of the last century, 1890s and from there on, did industrial electrolytic processes for the manufacture of chlorine and aluminum, and rapidly thereafter derivatives of chlorine and I might say other metallurgical processes enter the technological field. Now, I would like to, may I have the first slide? I have to put my, I am going backward, which is a rather inefficient way to get to the slides. Yes. I first would like to remind you of what role electrochemical processes play in our economy. First, this is the absolute latest energy flow diagram of the United States. It was published in late October by the Lawrence Livermore Laboratory, and knowing the US Postal Services, I doubt that any one of you has received this yet. Now, what I would like to call your, is this sharp enough? It should be a good slide. Ah, no, it's not sharper, but they put the light out. Is it better? Okay, well, this total generation was use of primary sources was 75 quads. For those of you who don't know what a quad is, which probably includes the entire audience, a quad is 10 to the 15th BTU. Now this is not a very pleasant number, but I will translate it into kilowatts. That is, one quad is 300 million kilowatt hours. 300 billion kilowatt hours, sorry, 300 billion, okay. Now what is interesting here that the total 75 increased from 70 in 1970. So in 10 years, the total use of primary energy sources increased less than 8%. It's about 7.5%, but the electric generation increased by 20%. Now, what is the significance of this? How did it increase to begin with? Well, the nuclear is the most important component. Hydroelectric increased slightly. Geothermal increased by a factor of 3, but that didn't make so much difference. A little bit of increase was due to coal. There was a shift from petroleum to coal and to natural gas. This figure in 1970 was 15 or 16. Now, the electric generation, of course, after distribution losses, we go into industrial use and we go into residential use. A very remarkable fraction of this industrial use goes into electrochemical processes. And this gives the story at least until 1970. Notice that in 1902, from which time the first statistics are available, there was a very modest beginning. In the beginning, 1 or 2% of total electrical energy was used for electrochemical purposes, but by the 50s, we were up to almost 7% just for aluminum and chlorine alone. Today, we are back to between 5 and 6% for chlorine and aluminum of the total, for all purposes, electrical energy generated, but well in excess of 10%, much closer to 15% for the industrially used electricity. So we are talking about a very important component in the national economy, and if I couple this with the trend that you have observed as we went from 70 to 80, and with the absolute necessity that nuclear power will be expanding, whether you like it or not, and I have serious reasons to believe that most of you like it here, there will be a further shift towards electricity being the primary source available to the industrial consumer. I would like now to briefly run through a number of characteristics of electrochemical processes which may be very familiar to those of you who are in the industry or in the academic field, but not to those for whom this discussion is new. Typically, electrochemical systems are reversible, or at least many are. They are characteristically, transformations are characteristically occurring with high material and energy efficiency, certainly very high efficiency compared to ordinary chemical transformations, which are usually completely irreversible in the thermodynamic sense. They may occur with very high selectivity and purity. A separation factor of 10 to the 6 is not at all unusual in one step. They are capable of extreme reaction conditions corresponding to high temperature and especially to very high pressure. It is possible to generate reduction conditions or oxidation conditions in electrolysis that correspond to 10 to the 30th or 40th powers of atmosphere's pressure of hydrogen and oxygen. Certainly no other reaction environment is capable to produce these extreme conditions. And it is, of course, illustrative of this, that fluorine and lithium at the two ends of the periodic table are produced solely, absolutely solely by electrolysis. One terribly interesting feature of electrochemical transformations is that it is not only suitable for producing a bulk chemical, but within a single reaction step, it may yield a product, a metal, for instance, or an alloy with a predetermined structure and surface finish. It may be a metal that is deposited with a mirror bright finish and a very thin layer. Some not so pleasant aspects are low space-time yield. The amount of reaction per unit time coming out of a box is usually not as large as out of a chemical reactor. That usually indicates a large multiplicity of reactor units. It is not unusual to go into a plant where there are literally thousands of electrochemical cells individually manifolded and fed and products removed. And they usually have, as a consequence, a large footprint. They require large acreage. There are very good reasons why electrochemical reactors are built low and not tall. Reasons that I do not wish to discuss now because it would take too much time. Now, one terribly interesting and useful aspect of electrochemical systems that you can, when you scale them up, you end up scaling them up by repeating reactor units. You don't just increase size indefinitely, but they can be scaled down. Now, ordinary chemical reacting systems usually cannot be scaled down well, especially not in the energy storage or conversion field. But you can make efficient energy converters and storage devices that are the size of a pea or smaller. Now try to imagine by what other means would you store efficiently electrical energy or mechanical energy for that matter, if not by electrochemical means. So this downward scaling possibility is a very important aspect of electrochemical reactors. Finally, generally, electrochemical reactors are environmentally benign, and in fact, electrochemical techniques may be used to remove noxious effluents. There are numerous techniques by which this can be accomplished. I like to go through, for the sake of those who are not in the field, and for those who are in the field, to be impressed again about the breadth and opportunities that our field offers, but a gamut of industrially, economically important processes that electrochemical technology covers. The largest variety of applications is in the electrometallurgical area, where a dazzling array of techniques are used today in literally tens of thousands of locations and applications. Electrowinning, or the recovery of a metal from an ionic state, is very well known. Numerous metals are recovered, their primary recovery in this form. Electrorefining of many metals is accomplished this way. These are well-known large-scale industries. Incidentally, I might mention that with the exception of iron, essentially all metals in the periodic table are either recovered primarily in their primary recovery step by electrolysis or refined. And for that matter, if you want real good iron, you do it by electrolysis, or you should be doing it by electrolysis, or you will be doing it by electrolysis. Now, the shaping, cathodic processes, electroforming, typing, the first electrochemical processes were of this order, where gilding and reproducing of object in silver and gold, or from a less noble metal and then be covered by silver and gold. These were the first processes very widely practiced today. By electrodeposition, you can reproduce surface profiles with tremendous accuracy. As it is well known, the recording masters are made by electrodeposition. Among the anodic processes, the much more recent techniques of electromachining and milling have unique importance in shaping materials which are very hard to cut, like, for instance, refractory compounds or nickel-based alloys, which are a beast to machine if you can cut them at all. By electromachining, we mean a process which dissolves the proper shape by connecting the workpiece as an anode, and not ever touching the workpiece by the tool, and thereby not impairing its physical and chemical quality. Among the surface treatment, electroplating is, of course, the most known and sounds the least interesting to most people, in spite of its enormous economic significance, in spite of the tremendous ingenuity with which it is conducted, and its economic significance. What we do here is that we take a substrate for its mechanical properties, strength, and we cover it with a layer or a number of different layers of other metals to impart to it different chemical or physical properties. Modern life without electroplating would be absolutely impossible to imagine. I mention this here because electroplating is not a subject that sounds very elegant to a lot of people, but in fact it is a tremendously important field in our technology and of enormous economic significance. Now, among the anodic surface treatment, we have oxidation of artificial electrolytic oxidation of surfaces for optical or electrical properties and color. All the aluminum buildings that you see, aluminum-sided buildings, have been anodically treated, and practically any color can be today produced by very ingenious techniques. Many of these techniques, incidentally, have been developed in the last 1 or 2 decades. Finally, there are certain dissolution techniques by which effects can be achieved, like polishing, which would be nearly impossible by any other means. So much for metals. In the electrosynthesis, production of non-metallic materials, I will mention that, of course, chlorine is the most obvious product. Our civilization today would be very difficult to imagine without chlorine. It is the cheapest oxidizing, powerful oxidizing agent available to humanity. The byproduct of chlorine is the caustic potash and sodium hydroxide. The demand for chlorine or for caustic varies, and there are times when you want more of one or more of the other. I understand in many locations today the demand for caustic is higher. All of the fluorine is produced by electrolysis. An astonishing quantity per year is produced, 100,000 tons or in excess each year. And of course, I need not remind you that importance of fluorine compounds, which include polymeric materials, the perfluorinated ethylenes, and the solvents, the freon solvents and related materials. Electrodecomposition of water was practically the sole source of pure hydrogen before the war, before the Second World War. That was entirely replaced, or nearly entirely replaced, by hydrogen from hydrocarbons. But electrolytic water is, decomposition of water is returning. In the generation of deuterium oxide, electrolysis is one of the alternatives. And of course, ozone may be generated with rather high charge efficiency, if not stupendous energy efficiency, by electrolysis. Now, much lesser volume products are listed here. Metal oxides, their importance is not necessarily proportional to the volume in which they are made. Manganese dioxide is of enormous importance in primary and now, hopefully, in secondary batteries. Cuprous oxide, mercuric oxide used as catalyst. The regeneration of these reagents for organic oxidation and for halogenation. And of course, peroxyanions, which are still made, although peroxysulfate is no longer a sole source for hydrogen peroxide. This is a very incompetent and abbreviated list for electroorganic synthesis, of which the most important, the hydrodimerization of acrylonitrile to adiponitrile, is a famous Monsanto process, the most significant large-scale application of electroorganic synthesis. Of course, lead tetraethyl was made. One of the major ways to make lead tetraethyl was by this reaction. These other reactions are only indicative of the possibilities. Manuel Baser each year publishes a competent list of additional applications. These are, however, not as yet on the scale of the first two. Now, I would like to interrupt the review of electrochemical technology with a few graphs that I have taken from Theodore Beck, Ruggieri and Beck's excellent work that was developed under DOE sponsorship through Argonne Laboratories, and which is published in the 12th volume of the Advances of Electrochemistry and Electrochemical Engineering. Now, let's look at efficiencies. One of the good results of viewing of the energy shortage or threat of energy shortage of the last decade was that we started to be concerned about what is the efficiency actually with which we make industrial chemicals. Now, this is of course a thermal input for the Bayer-Hall process. This is for making alumina, and this is for the electrolysis cell. We end up with an 8.6% overall thermal efficiency. That is to say, if we take the energy and material here, the efficiency that comes out here is represented 8.6%. It sounds little, but I will make a comment on that later. Now, the magnesium process is shown here. Here you have to multiply this input figure by a factor of 3, because here this is already in electrical energy form, and the generation of electricity can be taken as roughly 33%, occurring with 33% efficiency. Now, the efficiency of these, the magnesium process is less than that of the aluminum. If you, I'm sorry. Here is the Alcoa's proposed and semi-works tested recovery of aluminum going through aluminum chloride melt, eutectic melt. This has, you will note, a 14.3 point efficiency, not quite twice as efficient, and requiring 1/2 as much, or nearly 1/2 as much total energy input per product here. If you go to a material like chloride, the efficiency becomes prohibitively low unless you are willing to credit, recover, and use hydrogen. You'll find this, the difference is roughly 2% versus 10% efficiency. Finally, I take an example from the work, from Beck's work, in which he calculated a possible synthesis plan for the electrochemical production of ethylene oxide. The efficiencies, the lines were drawn to roughly represent the efficiency relationships. The efficiency is very, very marginal. Now, all I want to tell you that while these efficiencies appear low, the chemical synthesis alternatives are much worse. It is quite typical for an ethylene or propylene, integrated ethylene or propylene plant to have an efficiency in the region of 1/2 to 2%. Returning now to other aspects of electrochemical technology, I will mention processes where we do not wish a chemical transformation, but just to separate physically mixtures. Electrodialysis is perhaps the best known. This is, for instance, electrodialytic desalination of seawater or concentration of saline solutions. Electrophoresis or endosmosis, deposition of dielectric particles from suspensions, dehydrogenous dielectric masses are practiced on some significant scale in industry. These electrically induced coalescence, selective flocculation, filtration, flotation are of more recent origin in their industrial applications, along with wastewater treatment, where a combination of these effects is really used. Going on to a field not very much discussed when electrochemical technologies is mentioned is a field of electrochemical devices, sensors, transducers, a whole gamut of these devices is manufactured, and annually I would place its dollar volume between, and I don't have an actual figure available, in the range of perhaps $200 to $500 million in the United States alone. 2 billion? Only those? Now, of course, I didn't think of the doctors. This part is 1.5 billion. So anything above this is okay? Yeah, okay. I thank you for correcting my overly. But am I not right that it is the 1.5 billion is a low?
$700 million worth of heart pacers in the United States.
Yeah. No, that includes the, yeah.
No surgical pacers.
Well, I will not in detail discuss batteries. That is in itself a huge field. But I do wish to at least clarify certain terminology, what we call a primary battery, a secondary battery, or a fuel cell. And I want to show you a very recent result of taking a hard look at what is ahead of us in this category. Of course, the area of primary batteries has shown the most remarkable innovations since the last war, in the last 20 to 30 years. And a tremendous variety of new systems have become commercially significant. And some of these are on your wrist, and some of them are imported from Japan. Now, this is can you adjust sharpness? Okay. I will not apologize for the small print. It is very unnecessary for you to try to read all of it on it. But I just wish to mention to you that along with Professor Jaeger, Dr. Adam Heller, and two others, we have reviewed and tried to estimate what is the situation with respect to advanced batteries for automotive traction and for central power storage. The interesting aspect of this list that it contains a tremendous number of new systems or old systems that have improved tremendously. And even the lead-acid battery has shown great improvements. The nickel-zinc battery, which conceptually has been known, of course, for, I don't know, 70 or 80 years, is indeed showing great advances. There are entirely new systems, like the zinc-chlorine, zinc-bromine battery. There are systems of at least conceptual interest using aluminum as a sacrificial anode for automotive traction with extremely high, potentially extremely high specific energy. What is here in this last column are the ultimate possible costs as we see it, and they look very encouraging. This is, of course, in 1981 dollars, so it's already too low. But the small print here is not important. What is important is that there are something like 10 or 12 systems here which show sufficient promise that, in our judgment, that we should keep working on them. That it is impossible at this stage to say that just don't touch it anymore, it's not interesting. The other list includes high temperature rechargeable cells, high temperature being, you know, in the range of 350 to 500 degrees centigrade. And here I only wish to mention that all of these systems are new. All of them are less than 20 years old. And several of them are very, very promising. This is a Ford system. This is the argon calcium instead of lithium. This is argon battery. This, I believe, is GM. This is Dow Chemical, and this is ESB. The already proven performance includes lifetimes into the 15,000 hour range. 15,000 hours is almost 2 years continuous. And the specific energies and specific powers already tested on relevant cycles, namely some urban or suburban driving cycle, are certainly in the range where a modestly powered gasoline-driven vehicle's performance could be duplicated. The projections are all most intriguing, both in terms of specific energy and specific power, and the costs projected are acceptable. Whether these projections will materialize will depend on the willingness of both government and industry to take further risks in developing new materials for the containment of reactions which at these temperatures it is not easy to achieve. Now I wish to mention, may I have the slides up for a minute, please? I wish to mention that electrochemical science and engineering, electrochemical engineering science in the past decades has brought forth very respectable results, some of which have already penetrated technology. This was accomplished with relatively modest support from government and equally relatively modest support from government, from industry. I will not take it on myself to try to illustrate the achievements of electrochemical science, for which there are much more eloquent spokesmen around, but I wish to make just a very few comments on what advances have been made in the engineering science area in the last few decades. I think that we are quite capable today of scaling up processes without having to going through that extremely painful gradual increase in size. We can predict what happens when process variables, input variables are changed, when distance relations are changed, when a velocity is changed, when a current density is changed, simply because we understand better the scale dependence of electrochemical phenomena. Now, that scale-dependent phenomena, the transport phenomena, ionic and other material transport, and transport of heat, and of course transport of charge. Now, if I may, I want some more slides, please. Yes. I show you this slide to indicate the type of results and type of background that has been achieved in recent years, and I show it to you because it has some local significance. Your own Professor Uziel Landau has done this. It represents the dependence of the limiting current or mass transport rate, which is proportional to the Sherwood number, on flow properties and solution properties, diffusivity, and channel dimensions when you have a parallel plate reactor. This covers the entire laminar range, and the actual line drawn through here by regression and the exponent obtained corresponds very well to theoretical expectations. What is very unusual in this result is that the data and the technique is so accurate that non-electrochemical chemical engineering has taken over the techniques by which electrochemists are evaluating their scale-dependent processes. If any one of you is familiar with the chemical engineering literature and the tremendously ambiguous scatter of data that you obtain in heat and mass transport studies, he will appreciate the precision here. Now, to cover that range, the previous slide covered this little line here. This covers now a huge range up to well over Reynolds 100,000 of turbulent flow with excellent accuracy, covering a large number of Schmidt numbers, which of course is characteristic of or characterizing the diffusivity and kinematic viscosity of the system. So with this type of correlations, which are incidentally, which have sound theoretical basis, which cover a very large range of variables, for instance, channel type electrolysis cells can be designed. We can predict what happens if you change velocity, what happens if you change a distance, a temperature, a solute concentration. And furthermore, it is possible to tell what data and under what circumstances should be obtained in the laboratory. So the translation of laboratory results into plant practice is not nearly as risky, as mysterious a process as it used to be. Another area which is very critical to the design and operation of electrochemical systems is a distribution of current. Since the rate of electrolytic process, electrode process is proportional to current density, the current density distribution along an electrode surface tells what, for instance, the thickness of a metal deposit will be along an electrode, or it will tell if you have a battery pore. For instance, you might regard this representative of a pore within a battery plate. It will tell you at what rate the reactant is going to be used up and how that use will distribute in the pore. Not at all an irrelevant problem. Now, what this shows, this is a distance along this electrode here, which is 0.9 when the whole length of the pore is 1. And what this slide tends to illustrate, that depending on the single characteristic dimensionless parameter that characterizes the distribution of current in this pore, what will the distribution be? And the dimensionless number is, people used to accuse me that I put this down as Tobias number, but it is in fact, I put it down for throwing power, but since then the IUPAC named it, I might add with some pride, at my suggestion, it was named after Karl Wagner, who was not the first who suggested it, but the first who understood it. And then not only that, he had the patience to explain it to us. And then we, of course, told our students that it is trivial. So this is kappa, a conductivity, beta, the pre-logarithmic factor in the Tafel relationship, which connects overpotential to current. L is the characteristic dimension of the system, which in this case is the length. I is the current density. But there is quite a bit of message in here. This is dimensionless, incidentally. It says that as this number increases, the current distribution tends towards uniformity. If it is infinity, the current density would be uniform. It's a very simple reason why this happens, and that is that when this current this ratio increases, the surface resistance becomes large compared to the resistivity of the solution. Now it shows this for 1, this Wagner number 1, 3, and 11. Now this is a very recent result by Professor Prentice at Johns Hopkins, who in his brilliant doctoral thesis modeled, among others, sinusoidal surfaces. Surfaces which have a two-dimensional wave in them, sinusoidal for mathematical reasons because it is accessible for certain manipulations. And it describes how an initially sinusoidal wave of this amplitude and wavelength ratio behaves as deposition proceeds. This is a moving boundary simulation in which at each instance Faraday's law is applied and the boundary is advanced by an appropriate degree and a new boundary drawn. The simulation in this case includes mass transfer resistance to this sinusoidal wave. It's not just a primary current distribution. It includes the fact of that there is a boundary layer here, and the ions have to diffuse through that. Of course, they find the path here shorter than here, and an exaggerated growth of this sinusoidal profile occurs. I now would like to show you a very short film clip in which such moving boundary systems are illustrated. And yes, will you please show the movie? And this is a computer-generated motion picture. First, we show a corner where we are dissolving this anode. And of course, there is a high current density in this corner. And as you dissolve this away, you will notice that that corner diminishes. Now, this is a sinusoidal profile as you advance a cathode towards it. And the question we raise is how much of the metal does have to be dissolved to reduce the amplitude to 1% of its original value. And a remarkably large quantity of it has to be dissolved. Thank you. Stop the movie, please. Those of you who want to see the rest of the movie will have to come Wednesday. And I would like to go back to my slides. Okay, this mysterious picture depicts what I call a micromosaic electrode, which was made by IC techniques onto a silicon wafer. Each of these lines here represent aluminum conductors that are embedded in silicon dioxide and that lead to the center of these squares. And the squares themselves are platinum. And these lines between the squares represent SiO2, and they are 2 microns thick, or 3 microns, I believe. In any case, each of these squares has a dimension of 100 by 100 microns. Now, this micromosaic electrode was made by my coworker, Mr. Dennis Dees, for the purpose of looking at electrode phenomena on a spatially small scale. For instance, we look at gas evolution and we try to resolve the events around a bubble, including the field around it, including supersaturation, and including mass transport to the electrodes surrounding the bubble when it rises. Now, I only wish to show you that here is the 10 by 10 matrix of platinum squares, and out here are electrodes on which we are reducing ferric to ferrous chloride. At the same time, when at this segment, we are generating a hydrogen bubble. Now, the hydrogen is generated on a horizontal platinum surface, and it gets nice and big and fat. This bubble is 1.5 millimeters in diameter, which for electrolysis is a huge bubble. Electrolytic bubbles are small and nice, not these big floppy things like you see in distillation columns. But it gets big because because they are on a horizontal electrode, and you grow the bubble under nearly equilibrium conditions, and it will finally separate under the influence of buoyancy force. And at that time 0, here is the separation. We look at the current that occurs on this square due to reduction of ferric chloride. And with this technique, we establish what sort of hydrodynamic event must have occurred when the bubble separated to cause first a small increase and a very rapid decrease in rate of transport to this segment. This is a free convection situation generated by a bubble separation, which I showed you to illustrate the analytical experimental techniques that have become available through solid-state devices by which we can look at phenomena like electrolytic gas evolution in really great detail to explain the behavior of gases during electrolysis. Thank you. I don't want more slides. The lights can be put on. I attempted in the preceding 50 minutes to paint you an overview of the outlines of electrochemical technology and mention some of the innovations that have occurred. There is a tremendous array of new materials that have become available for active and passive components in cells, and these perhaps make the biggest difference. I will mention among these the ruthenium oxide and similar metal oxide electrodes, which allow entirely new cell designs. I mention here the use of solid ionic conductors, of intercalation positives for batteries, of polymeric ionic conductors, electronic conductors, and intercalation compounds. And finally, a variety of polymeric materials which we can use for containment of reacting systems. The conditions for advancement of the technology are really excellent, and I am looking forward to an eruptive growth. The incentives, economic incentives, are all too obvious. We are able to translate laboratory results much more competently and efficiently and rapidly and reliably into economically viable processes. So it is, I think, a very safe prophecy to say that the coming decade or decades will see a major expansion of electrochemical technology, both synthesis technology, batteries, both for primary storage, fuel cells indeed, by all means. And I also think that the area of surface treatments will further diversify and grow.